Hi everyone. So in this lecture we're gonna continue with some of the properties of the Fourier transform. And so if you recall, we had these two equations as the Fourier transform pair. And so where x of j omega was the integral of x of t, um, complex exponential, and x of t could be found from 1 over 2 pi integral of x of j omega, another complex exponential. And as you can see, these two integrals are kind of have a similar format to them, where they are being multiplied, the functions are being multiplied by complex exponentials and then being integrated over d of omega or d of t. And so this creates a dissimilarity, kind of brings some interesting things to the Fourier transform. That if, for example, we consider that we give a square wave to the signal x of 1 of t, and then take the Fourier transform of that, what we get is a sinc function. So we know that, right, from the previous examples that we did. Now, if we give this sinc function, right, to as the time domain and then take the Fourier transform of that, the interesting thing that would happen is that we would get a square wave, right? So this is very similar to what to the case above, but when we swap these twos. But the thing is, there are differences in them. So for example, here we have w divided by pi is the magnitude here, and then minus w, and w is the width of this square wave here. And but this is not the case for the case above, right? So we have a similar pattern. So that if we have a sinc, we get kind of a rectangular here, and if we have a rectangular, we get a sinc here. But the actual values are not the same, and that's because, well, this is the exponential here has a minus here in it, whereas in the above it has positive in it, and here we have a 1 over 2 pi in the actual equations as well. So this is kind of the duality property, and what it basically says is that if we have x of t and then we take the Fourier transform of that, we can get x of j omega. And so if we bring x of j omega down here and then replace omega by t, so we'll have x of jt. Then if we take the Fourier transform of that, we take x of t here, and then we replace t by minus omega, and then multiply that by 2 pi. And so this would be the Fourier transform of that. And so the reasoning for that I've illustrated here, so you can go through it if you're interested. And so the example, if we want to do so, the rectangular that we showed above, if we have a rectangular of t divided by capital T, so we'll have a sinc of omega capital T divided by 2, right? So if we give it a rectangular, we get a sinc. Now, if we give a sinc, we showed above that we get a rectangular, right? So how does the, as we said, there are differences between the peaks and, you know, the zero crossings and all that. So how do we find those? So we find those by replacing omega with t. So we replaced omega here with t. So sinc of t, capital T divided by 2. If we take the Fourier series of that, it will be 2 pi multiplied by, and so this t here, we brought it here in the denominator. So t was here, so but we could bring it in the denominator there, right? And so for the rectangular, we are replacing t by minus omega. So here replace t by minus omega. We have rectangular of omega divided by capital T. Okay, so this is one example. So another thing is the symmetry property in Fourier transform, and where if x of t gives us x of j omega, its convolution gives us convolution of minus j omega, right? X of minus j omega, the Fourier transform of that. And if x of t is real, then the real part of x of j omega is even, and if x of t is even, x of j omega is even and real. If x of t is odd, x of j omega is imaginary and odd. You don't need to memorize this, as I said before. The exams and the final exams and everything is open book, so you can just have these properties written next to you in a table, or use a table to just look and use them. Next we have the convolution. So in the convolution, if we have x1 of t multiplied by x2 of t, and we take the Fourier transform of that, Fourier transform would be 1 over 2 pi x1 of j omega convolute x2 of j omega. And if we have x1 of t convolute x2 of t, what we have is this interesting form of the multiplication of x1 of j omega and x2 of j omega, right? So if we have a linear system, for example, y of t, and then the impulse function response of that system is h of t, then so y of t is equal to h of t convolute x of t, right? So y of j omega, its Fourier transform of y, is equal to the Fourier transform of h multiplied by the Fourier transform of x of t, right? And from that you can find y of j omega, and if you want to find y of t, then you can just find the inverse transform of that in order to find y of t. So that's another form to way to get y of t by just using the Fourier transform. So next we have the x of t equals sine of omega t, rectangular of t divided by capital T. So this is an example, and we have two multiplications here, and we want to find x of j omega. So what is x of j omega? So this is the multiplication of two functions. So what we can do is that find x1 of j omega, x2 of j omega, and then convolute these two and then divide it by 2 pi. Right, so that's exactly what we're gonna do. So x of t, if we take the Fourier transform of that, is gonna be 1 over 2 pi Fourier transform of, okay, so this is sine of omega naught t, and then convolute Fourier transform of rectangular of t divided by capital T. Okay, now we know that sine of omega t can be written as this function here, e to the power of j omega naught t minus e to the power of minus j omega naught t divided by 2j. Okay, now the Fourier transform of e to the power of a complex exponential, we know that we can write it in terms of this 2 pi multiplied by delta of omega minus omega naught, and then when we divide it by 2j, we'll have pi over j delta of omega minus omega naught minus delta of omega plus omega naught for sine of omega naught t. And then the Fourier transform of the rectangular of t divided by capital T would be a sinc function of capital T multiplied by sinc of omega t divided by 2, which we know from before. Now, and then the whole thing divided by 2 pi. Now, what we do is that we bring this convolution inside these brackets and then convolute each one of these. So convoluting a phase shifted impulse function by a function, we can just directly replace what is inside the brackets of the delta function and then replace it inside of omega, right? So we covered this in the previous lectures when we were talking about how to convolute an impulse response with another function. And so therefore the end answer for this would be capital T divided by 2j sinc of omega minus omega naught t divided by 2 minus sinc of omega plus omega naught t divided by 2. Okay, so let's look at another property, which is the Parseval's theorem. And we know that the total energy in signal is calculated in time domain from this, right? Now, the total energy of the signal in time domain is equal to 1 over 2 pi, the total energy of the frequency, its frequency components. So integral of minus infinity to plus infinity of x of omega to the power of 2 d of omega. And if we write it in terms of x of f, we don't need that 1 over 2 pi anymore. So so here we have integral from minus infinity to plus infinity of x of t. The total energy in time domain would be the total energy in the frequency domain here. And so that's the case for this. Now, so we're done with the Fourier transform, and we introduced the properties, what was left from the previous lecture. Now, we want to introduce a new concept, which is the Z transform. In Z transform, well, in the Fourier series and in the Fourier transform, really, what we were dealing with were continuous time. And we used its capabilities is for continuous time signals. Now, the Z transform is another tool that we're going to introduce that is applicable to discrete systems. Okay, so Fourier transform and the Z transform are kind of special cases of the Laplace transform. And so now let's see what actually the Z transform notations and its function looks like. So a bilateral Z transform is written like this. So we have the Z transform bilateral of a function f of n, or we can write it as or note it as f of b of z is equal to sigma from n minus infinity to plus infinity of f of n z to the power of minus n. So this is the function that we are taking a Z transform of, and we're just putting it inside this equation. So we're just multiplying it by Z to the power of minus n, and then taking a sigma of that. So note that this f of n is a discrete time signal, but the actual Z transform of that is a function of Z and is not discrete time discrete anymore, right? So when taking a Z transform of a signal, that signal itself is a discrete time, but when you take that Z transform, because it's a function of Z, it's not discrete anymore, okay? Which is what we're saying here. Now let's look at one example here. So we have an example of a discrete time signal x of n, 5 delta n plus 2, 3 delta n plus 2 delta n minus 1, and x of n is a set of 5, 0, 3, and 2, and where 3 is the where delta n is plus 1, right? Plus 0. And so 5 is for delta n plus 2, 0 is for the 0 multiplied by delta n plus 1, right? So that's why we have 0 here. And then 3 and then 2 that we wrote here. Now, if we want to take the Z transform of x of n, what we have is x of z is equal to 5 z to the power of 2, because this is for delta n plus 2, right? Plus 3z to the power of 0 plus 2z to the power of minus 1. Okay, so this is the Z transform of that. And if we want to do another example, we have x of n equals a to the power of n u of n. Now, if we take the Z transform of that, so this is the actual formula for taking the Z transform, and all we need to do is to replace xn in this equation. By doing that, n was from minus infinity to plus infinity. Because we have u of n here, n becomes from 0 to plus infinity, a to the power of n, z to the power of n. Okay? And so this equals sigma from n from 0 to infinity, a divided by z to the power of n, because this is minus n, right? So a divided by z to the power of n. Now this is, so how do we find these signals? This is a geometric series signal, and you should kind of know how to solve these kind of series and then find the answer. But for recalling, I've put in this box how to actually solve these. So for example, if we have a sigma of k from 0 to infinity r to the power of k, and the magnitude of r is less than 1, so this is important, because if it's higher than 1 or equal to 1, this won't have a finite value and it will be infinity. So if this holds, then the answer would be 1 divided by 1 minus r. And if we want to find k from 0 to m, a finite value, not infinity, r to the power of k, which is kind of a general case of this that we showed above. So it will be 1 minus r to the power of m plus 1 divided by 1 minus r. So if we see here m in the above case, m is a special case of the below case, right? M is going to infinity here. And if m goes to infinity here, r to the power of infinity when r is less than 1 will be 0. So that's why this has to hold, right? Because if this does not hold and if r is higher than 1, then this will be infinity, right? R to the power of n plus 1. But if the magnitude of r is less than 1, r to the power of infinity would be 0. And so if we have another thing would be if we have k from m to infinity, not 1, but m when m is greater than 1, greater than 0, sorry. Then r to the power of k, then we can find this from r to the power of m divided by 1 minus r. Okay, for this case here, we have n from 0 to infinity, so it's the first case that we showed here. So the answer would be 1 divided by 1 minus r when this holds. So what we get here is 1 divided by 1 minus a divided by z. A divided by z is the r factor here, right? And if r, the magnitude of r is less than 1, a divided by z is less than 1. So we can rewrite this as the z transform of x of n is z divided by z minus a if the magnitude of a is less than the magnitude of z. Okay, so this is important. So this is the region of convergence for us. And so if we want to show this in the z-plane, what points in the z-plane will actually converge and have an answer in the z-transform, okay? So if we have the real part and the imaginary part, and we draw a circle here, as you see, with a radius of a, anything, so if z, the magnitude of z is greater than a, then this will hold. So if we are outside of this circle, because if we are outside of this circle, then the magnitude of z is greater than the magnitude of a, right? Because this is the z plane. So any point here is the z plane. So this would be the distance, the magnitude of the point z, right? And it's obviously greater than a because it's outside of this circle. And this is the region of convergence. Okay, so we note this as the region of convergence. Okay, so let's do another example. So if we have x2 of n is equal to minus a to the power of n u of minus n plus 1, and we want to find the z transform of this. So I've written here how to find the z transform first. You can, I think, for your practice, first do the z transform of this, and then you can just double check your answer from here. And what the interesting thing that would happen is that the z transform of x2 of n is exactly the same thing that we found for the z transform of x1 of n. So the previous example here, a to the power of n u of n. So if you recall, we found z divided by z minus a here, and here also we find z divided by z minus a here too. However, what is different here is the region of convergence. So here, now, if z is less than the magnitude of z is less than the magnitude of a, or if we are operating within the circle here of the z-plane. So if we are operating within this circle, then this function would have a z transform that can converge. So the region of convergence is within this signal. So what we can conclude is that if we are given only the z transform of a signal, that's not a unique thing in order to find the actual signal, right? So the Z transform of a signal could give us two different signals. However, so if the Z transform is not, so this means that the Z transform is not unique without the region of convergence. So we need the region of convergence plus the Z transform in order to have in order for it to be unique, right? So this is what we are right now explaining. So if we have a to the power of n, u of n, we get the same Z transform. And if we have minus a to the power of n, u of minus 1 plus n, we have again the same Z transform. But the region of convergence, one is outside of that circle and one is inside of that circle. And usually the region of convergence will be of this following shape, right? Where the radius of the inner circle is A and the radius of the outer circle is B. And the radius of the inner circle A can start from 0, so it basically can be here, so it could cover all of this circle. And the radius of B could go until infinity, so it could cover everything outside of the circle. So for example, the radius of A here is, A, and the radius of B here is infinity, right? And right, so but in this case the radius of A is 0 and the radius of B is, whatever this value is. Yeah, so in this course, for the purpose of this course, we only consider signals that are 0 for n less than 0. So if n is negative, then the signal is 0. So for example, x of n is equal to u of n, right? So all signals basically, we're just saying that we're considering all signals multiplied by u of n. This is what it's been saying, telling us really, because u of n ensures that all signals that are negative will have a 0 value. Okay, therefore the region of convergence will be outside of the circle here. So we did an example above here, and we showed that if this is multiplied by u of n, right, so we get that region of convergence outside of this circle. So this would happen for the other cases if we have x of n is equal to 0 for n as a negative value. And if we want to take a Z transform of that, because the Z transform was from n minus infinity to plus infinity, now we know that if n is negative, then the signal will be 0, right? So we can just write n from 0 to plus infinity, x of n, z to the power of minus n. Okay? And so it becomes a unilateral Z transform, which we call the Z transform. However, the textbook calls the bilateral Z transform as the Z transform. So when you're reading the textbook, note that when they talk about the Z transform, they mean the bilateral Z transform. And okay, so let's look at some of the kind of pairs between specific signals, discrete signals that we get, and then what their Z transform would look like. So if we have an exponential signal, a to the power of n u of n, the Z transform of that, we showed that it's going to be Z divided by Z minus a, where the region of convergence is this. This is important. When you're doing the Z transform, always show the region of convergence as well. So what about the impulse function? What's the Z transform of the impulse function? Well, we're going to put the Z transform of the impulse function into the equation here. And so we know that this only has a value at n equals 0. So 0, we put z to the power of 0 is equal to 1. And so the region of convergence here is for all z's. For all z's, the impulse function, the Z transform of an impulse function is going to be 1. How about a time-shifted impulse function? Will it be the same? So a time-shifted impulse function, if we put it inside here, this will only have a value at n naught. So this will have a value at z to the power of minus n naught. So what's the region of convergence here? So the region of convergence is not all the plane right now. It's because this is equal to 1 divided by z to the power of n naught, right? So z cannot be 0. So that's the only one point that does not the region that the Z transform does not converge. And so Z has to not be. So for if we're talking about the impulse function, it covers all the Z points. But if it's a time-shifted impulse function, it's all the Z points, but not zero. But not only not the not zero. So what about the step function? So if we have the step function, it will be Z divided by Z minus 1, where Z, and the proof of that is shown above here, where the magnitude of Z has to be greater than 1. And what about sine of B of n, U of n? So I've written the, so I think it'll be a good practice for you guys to do this, both the sine B of n, U of n, and the cosine of B of n, U of n. And then the answer for that, the region of convergence is as shown here. And the answer for that is like this. I've also shown the proof for sine of Bn, U of n, which you can double check with your answers when you do this practice yourself. And for the cosine of Bn, you can just, it's very similar. You can follow the same pattern. And so one thing to note is that a to the power of n, U of n has a Z transform. However, a to the power of n itself does not have a Z transform. So note that all of these signals that we talked about here, we really consider the case where this signal here is being multiplied by U of n. And this signal here is being multiplied by U of n here. Where what this basically means that we're only considering the signals that are n 0 and positive, and when n is negative, then this would be these signals would be 0. Now let's look at some of the properties of the Z transform. Well, the first one, which similar to the Fourier transform and all of that, we have the linearity, where we say if we take the Z transform of F1 is F1 of Z, F2 is F2 of Z, then if we take the Z transform of A multiplied by F1 of n plus B multiplied by F2 of n, it equals A F1 of Z plus B F2 of Z. And A and B are constants. And so for the time domain, convolution, if we have x1 of n convolute x2 of n, we have x1 of z multiplied by x2 of z, which is interesting. But however, for the x1 of n multiplied by x2 of n does not give us anything similar to x1 of z convolute x2 of z. So we had this case in the Fourier transform, but this does not hold the below case for in the Z transform. So the only thing that does hold in the Z transform is this above equation, which if we have a convolute of two signals, x1 of n and x2 of n, then the Z transform of that would be x1 of z multiplied by x2 of z. Now let's look at the time delay. How does the time delay look like? The time delay we just multiplied. So if we have fn minus naught, u of n minus naught, then it would be z minus n naught, right? F of z. So if we have a unit delay, it would be z minus naught. The function would be multiplied by z minus 1 to the power of minus 1. So let's do an example here. So let's say we have a set of numbers for the signal x of n, 1, 2, 3, 1, minus 2, and so on. And x1 of n is equal to x of n minus 2, u of n minus 2. So when we're delaying by 2, what we're actually saying is that we're introducing two zeros as the first value and the second value. Okay, so this is what we're really introducing here. So the first value and the second value is 0. So what happens is that we're shifting this 1 by 2, right? So the x2 of x of z would be the summation of x1 of nz to the power of n, right? So 1 here really starts now at n equals 2. So this would be 1 multiplied by z to the power of minus 2 plus 2 z to the power of minus 3 plus 3, z to the power of minus 4, minus 1, z to the power of minus 5. You get the idea. So we shifted the whole thing by 2, and by shifting the whole thing by 2, we're really multiplying this z to the power of minus 2. So that's z to the power of minus n that we had. So if we have a shift of time delay by n naught, then we are multiplying z to the power of minus n naught to our actual x of z. Okay, so how will the time advance properties work? So if we have fn plus naught u of n, and we don't want any value for the negative, right? So if we have f of n as 1, 2, 3, minus 1, minus 2, and so on, so what we're doing, if we're shifting or advancing by 2, then what we're doing is that we're omitting these first two values. So we have the same kind of structure as z to the power of n naught. So in the time delay, we had z to the power of minus n naught. Time forward, we have z to the power of n naught here. But instead of multiplying it by f of z here, we have, because f of z, we're reducing the first two values here. So what we need to do is write this multiplies by f of z minus the first values that were omitted. And the first values that were omitted were n naught values, right? N from 0 to n naught minus 1. Because 0 to n naught minus 1 were the values that were omitted. So fn z to the power of minus n. So that's why we have this subtraction here. Okay. Next, we have the time expand. So if we have f of n divided by capital N, we have f of z to the power of n here. So if you have fn a to the power of n u of n is equal to z to the z divided by z minus n, which we showed as the exponential. Well, we showed this above, right? Now, if we take f of n divided by 2, all we need to do is to write f of z to the power of 2. So we write z to the power of 2 here. Z to the power of 2 divided by z to the power of 2 minus a, and the region of conversions would be this. And I forgot. So this is for n capital N positive. So the scaling of in z. So next we're gonna look at scaling in z. So if we have a to the power of n here, so this is not a constant value anymore, and multiplied by f of n, then the z transform of that would be f of z divided by a. So if we have, for example, a to the power of n sine of b and u of n, then we have the same function as we did for the sine of bn, but for all z's, we're going to replace them by z divided by a here. So z divided by a and z divided by a, which we can simplify as this. Now, what about multiplying by n? So we have n multiplied by f of n. We're basically taking the z transform of f of z and then multiplying it by minus z. Now, there are two theorems as the initial value and the final value theorem, where if we want to find the initial value of f of 0 and the final value of f of 0, we can find them by taking the limitation. We can find the initial value by taking the limitation of f of z when z goes to infinity. And if f of infinity exists, that is, f of infinity is a finite value, then we can take the limitation of z minus 1 f of z, where z is going to, the limitation of z is going to 1, and then that will be the answer to the finite value of f of infinity, if f of infinity it actually exists. Okay, and so these are some of the properties. Okay, so now the application of Z transform in discrete systems. So how do we actually apply the Z transform in discrete systems? So let's consider a case where we had a difference equation. And if you recall, we introduced difference equation. We had the y terms on the left-hand side and the x terms on the right-hand side. Then multiply that by some constants, a0, a1, and then b0, b1 to bm, right? And then if we take the z transform of this, what would happen is that we would get a naught y of z, a 1 y of z, z to the power of minus 1, plus until a n a z to the power of minus 1 y of z. The same thing we have for the right hand side, but instead of y of z, we have x of z. So in all terms of the right hand side, we have x of z, therefore we can take x of z out of the sigma, and in all terms in the left hand side, we have y of z. So we can take y of z outside of the sigma here, and we have sigma of ak z to the power of minus k on the left hand side, and we have the same thing on the right hand side, but the boundaries would be different. So the boundary here would be a capital N, the boundary here would be capital M here. So now y of z from this equation here can be written from b naught plus b1 z1 z to the power of minus 1 b2 z to the power of minus 2 until bm z to the power of minus n divided by a naught plus a1 z to the power of minus 1 a2 z to the power of minus 2 plus a n z to the power of minus n, multiply the whole thing by x of z. So as you can see here, this division here does not depend at all on the input. So, and it's, well, it's determined by the characteristics of the system. And we call this h of z, which is really the transfer function of the system. So y of z is equal to the transfer function of this system multiplied by x of z. So this shows us that any input that we can take a z transform of, we can use this function in order to find its output. So if we can take the z transform of an input of a difference equation, so we can just use this function here, y of z is equal to h of z multiplied by x of z, in order to find its the inverse, no, the z transform of its output. And yeah, okay, thank you very much.